Bismillahirrahmanirrahim. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. I'm Madam Habibah Usop alias Yusuf. I'm going to teach Physics 1, Chapter 1, entitled as Physical Quantities and Vectors. Before we begin our lecture, please be reminded that we are always have to be humble and always remember that all knowledge coming from Allah, so we have to ask Allah for his guidance and understanding of the knowledge given. Alright, so let's begin our lecture. Why you have to learn physics in the first place? Actually, physics is the study of the basic components of the universe and their interaction. What is the basic components of the universe? Of course, we're talking about the human being, the surrounding of the human being, the earth, the air, all the living things, non-living things, and that is for microscopic point of view. The bigger or the macroscopic point of view, the earth, the Milky Way, the other planets, the sun, etc., etc. We have to learn about the components of the universe and their interaction. Why is it so? Because we are the Khalifah. We are asked to manage the universe according to the nature that Allah created them. So basically, theories of physics have to be verified by the experimental measurement. Most of it can be verified by measurement. If it cannot be verified by measurement, some of it can be analytically theorized based on simulation. Alright, so this is our textbook, College Physics 12th edition. The author and also the company produced the book. Okay, so let's begin with the standards of length, mass and time. So standards, why we need to have standards? Okay, because it going to be readily accessible, possess some properties that can be measured reliably, yield the same result every time we repeat, it does not change with time. So that is why we need a standard. So the most commonly used by us is SI unit, right? So physical quantities, anything that the measurement that we've done is one that can be measured and consists of magnitudes and units. For example, measuring a length. This is the length of the paper here. It's a kind of physical quantities representing the character of the paper. Alright, so if we take a look on the signboard here, what does that mean? So this is a speed limit, right? So the vehicle cannot exceed 70 km per hour. So it has magnitude and also unit. Okay, so what about this? This is normally for vehicle, not more the height of the vehicle cannot be more than 4.5 meter. Normally this is for bridge, isn't it? Basic measurement in study of motion or mechanics. Length, talking about how far. Okay, normally question involve being able to measure the distance between 2 points. If the question stated about time, to answer the question of how long did it take. Okay, and then for the mass is a measure of the amount of the substance of stuff. This is a common verse or a phrase that used in physics. Okay, now let's take a look on the basic quantities. The basic quantities are classified into two types. Okay, base quantities and derived quantities. Okay, so what is a base quantity? Is like just like the brick. If let's say we want to build a house, of course the brick is the mass, isn't it? This is a basic building block of a house, right? What is the derived quantity? The derived quantity is like the house that was built up from a collection of bricks. From the combination of the basic quantity, we have the derived quantity. Hopefully it is clear what is the difference between basic quantity and derived quantity. Let's take a look on SI unit. Okay, we have 7 base quantities. This is a SI unit of it. Oh, it is shifted. Okay, the symbol of it, meter, the symbol unit of it is m, isn't it? And then kilogram is kilogram, time, second, electric current, ampere. For the temperature, it's Kelvin. The symbol is capital K. Amount of the substance, mole. And luminosity intensity, basically this is talking about the brightness of lights. Okay, it's candela, symbol or unit of it is CD. So let us refresh with your prior knowledge on the derived quantities. Okay, so for this one, defining area. What is the formula for the area? Area normally we symbolize as A, where we have width normally times with the length, isn't it? So in terms of units of the area, normally it is in terms of meter square, right? Because okay, the units is for width is meter, the length as well meter. About the volume, normally the symbol is V. It is a common is width times length times with the height, right? So the unit of the volume normally is gonna be meter cube as a unit of it. And for the density, the symbol is rho, normally mass over volume. Alright, and the unit of it, okay, the unit of it going to be kilogram per meter cube. Okay, and this is for speed, for acceleration, for force. Let me do it, few of it for you. Speed symbol V, equivalent to distance travel over time taken, which give us the unit of it is meter per second. And for the acceleration, A equivalent to delta V over delta T, change in V over change of time taken, or time taken to have that change of V. The unit of it is meter per second square. And then for the force is actually equivalent to MA, right? So the unit of force will be kg m as negative 2. So for the pressure, P equivalent to F over A, the unit of it must be Newton over meter square, right? And work done is the force in the direction of the displacement, time with the displacement. So the unit for the work, okay, is equivalent to Newton dot meter. Or if you want to make it even bigger or in details, the Newton itself is kg ms negative 2 dot m, or you can simplify it into kg m squared as negative 2. And next for power equivalent to how much work being done over the time taken to do that work. Okay, so the unit of it will be joule. So this is also joule per second, okay, the same thing. Joule for the unit of work done, the same, or we put it joule over second, or the joule itself is kg m squared as negative 2 over s. Right now, let's move to subtopic 1.3, dimensions. Okay, dimension denotes the physical nature of a quantity, normally represented by three main measurement length symbolized as capital L, mass symbolized by capital M, time symbolized or represented by capital T. Normally for dimension, we use bracket, not parenthesis, okay? It must be bracket to denote dimension of a physical quantity. So when we talk about, let's say, area, okay, we know that the unit of it is meter squared. However, okay, since it's talking about length, because area is width times length, let's say, okay, so it is in term of symbol, in term of dimension, it is L squared. Okay, so this is SI unit, this is US customary unit, meter squared and feet squared. Right, so for volume, okay, for volume, the SI unit is meter cube. Okay, in term of dimensions, okay, dimensions it's symbolized because it's talking about length times width times height, isn't it? Volume, for volume, let's say V equivalent to length times with the width times with the height, isn't it? So all of the dimension talking about length, okay, a kind of length, all of it in unit of meter. That is why it is represented by L cube. Right, so for the speed, the unit is, the SI unit is meter per second. So meter in term of length, so symbolized or represented by capital L, and second is time, symbolized or denotes by the capital T. So the dimension is L over T. So goes the same to the acceleration, right? So it's going to be L over T squared. Okay, what is dimension? Dimension is talking about the physical, the character for a measurement, a measured value. Okay, so it talks about, if let's say you want to explain about a box, you want to explain about a box to your friends, okay, so you're going to say, okay, the box has the dimension of the width of what times with the length of what times with the height of what. You see, so talking about dimension, actually we are trying to explain about a physical quantity in terms of its dimension. Alright, so now by using the denotation of the dimension just now, okay, we are going to do dimensional analysis. This is actually a method, okay, a technique used to deal with the mathematical expression that relate different physical quantities. Okay, perhaps for example just now speed, right, or velocity just now is meter per second. One of it is talking about length, the other one is talking about time. So it's relate to physical quantities, two different physical quantities. Okay, so we're going to analyze the unit or the dimension, okay, of a physical quantities. Then dimension analysis make use of the facts that dimension can be treated as algebraic quantities. Means that we're going to deal it as a mathematics, okay, in simple mathematics. So the purpose of using dimension analysis, basically we can put it as three purpose. Find the units of an equation to check the homogeneity of an equation. What does that mean by homogeneity? It means that to check whether left side of the equation has the same dimension or units to the right side of the dimension. So means that we're also going to check in terms of units, is it possible to have that question? Is it allowed to use that question in terms of unit or the dimension? Because if you're putting A equivalent to B, it must be that the units of A and the units of B must be the same. The units of A and the units of B must be the same. Then we can use the equation equals to in between, right? This is the meaning of to check the homogeneity of an equation. And finally, to derive an equation from a given concept, we call it also as power law. So later on, I'll show you the details of this one. Okay. So example 1.1. Okay, we're going to analyze an equation given. So what is the goal? To check an equation using dimensional analysis. The problem show that the expression of V equivalent to V0 plus AT is dimensionally correct, where V and V0 represent velocities, A is acceleration, and T is a time interval. So, for those who just new to this expression, V not representing initial velocity, V representing final velocity. Okay, now onwards we are not using U anymore for initial velocity. Whether we are going to use V naught or sometimes we are going to use U actually now represented by V naught, or some of the books use V initial like this. Okay, for V final in secondary school, you are using V, isn't it? Now we are going to use V or V final. Okay, so let's proceed. So what are we going to do? Okay, if you see here, we have 3 items. Item number 1 on our left side, V, okay, equivalent to V naught. Item number 2 on our right side, plus AT. So when we are doing addition, okay, mathematically, the V naught and AT must be the same dimension, must be the same unit. Then we can add up them together. If they are not the same thing, the same dimension or the same unit, we cannot have the addition of the process here. So means that after you add up V naught and AT, it must be equivalent to V on this side. It means that the unit of the V and the unit of the product at this side must be the same thing. The dimension, this is on how to use dimension analysis. Okay, you have to put the symbol and then the bracket. Okay, the final velocity, the dimension of the final velocity equivalent to the dimension of the initial velocity, right? Because both of it are velocities. Okay, so which equivalent to L over T. For those who are putting, if you think you are slow, you better to put it like this. The dimension of V equivalent to the dimension of V naught equivalent to, put the SI unit firstly, meter per second. Then you substitute it with the dimensional symbol. Whenever you are replacing with the dimensional symbol, there is no more bracket. Okay, the dimensional symbol L T negative 1. It's just the same to this one, right? Okay, and now let's take a look on the other item here, AT. Okay, we are doing dimension analysis. That is why we need to put a bracket here. Okay, the dimension of the AT, this is actually a product of 2 things, right? A and also T. So for the A itself, it's L T over squared, T squared over T squared, times with the T, the dimension of it is T. So then, if you are slow, let's put it like this. The dimension of AT equivalent to the dimension of SI unit firstly, meter per second squared, multiple with the second. Give you, simplify it firstly, meter per second, isn't it? Then finally substitute it with the dimensional symbol L T negative 1. So means that the dimensional symbol for the V naught is the same to the AT. The dimension of V similar to the dimension of V naught, similar to the dimension of the AT. Therefore, it is dimensionally correct. Okay. So, take a look on the exercise there. Determine whether the equation of x equivalent to vt squared is dimensionally correct. If not, provide a correct expression up to an overall constant of proportionality. So, if provided answer here, it is incorrect. X equivalent to vt squared is incorrect. The correct one is x equivalent to vt. Let me show you on how to do this one. So the given expression to us, x equivalent to vt squared, okay, we're going to prove it that it is dimensionally incorrect. So let's check the left side firstly. Okay, it is x is position. The unit of it is meter. Okay, dimensional symbol of it is L. And now let's take a look on the right side of the equation. Vt squared dimensionally is SI unit firstly, meter per second, dot second squared. Simplify it firstly. M as 1, isn't it? Negative 1 plus 2, 1 only. Alright, so cannot be simplified anymore. Finally, we substitute it with the dimensional symbol LT. Then you see here the dimension of the, you see this one and you see this one, they are not the same. So the dimension of the x is not the same to the dimension of vt squared. Done. That is how. Whether you want to put it in terms of, you want to write down the dimension of the x is not the same to the dimension of vt squared, or you put it as like this, understood. Done. The correct dimension for the x equivalent to, okay, Vt, take a look whether this one is correct or not. The dimension of x is meter, SI unit, dimensional symbol L. The dimension of Vt, SI unit firstly, and then simplify it firstly. Correct, isn't it? Negative 1, 1 becomes 0. S power 0 means that 1, right? So we are left with M only. So L. So you see, this one and this one the same, right? Therefore, okay, the dimension of the dimension of the x is equivalent to the dimension of the Vt. It means that x equivalent to Vt is the correct equation. Okay. Example 1.2. Derive an equation by using dimensional analysis. The problem is find a relationship between an acceleration of constant magnitude A, speed v, and distance r from the origin for a particle traveling in a circle. So this is the beauty of dimensional analysis. Even though you haven't learned about circular motion, you in terms of mathematically can have a derived equation for any concept given. So let's do one by one. For the acceleration, the SI unit is meter per second squared. Okay, so the dimensional symbol of it, L over T squared. For the speed, okay, it's meter per second. So the dimensional symbol of it, L over T. Okay, and then for the expression of A in terms of the dimension, this is actually, let's substitute the T, okay, into with the V equation. L over T. What is the T in terms of V for this one? Okay, if the T is equivalent to L over the dimension of the V, isn't it? So the T here, okay, remember it's T square, right? So L over the dimension of the V, everything squared. So here we have, okay, V, the dimension of the V squared over L only, right? Simplify it to this, because remember the L here must be squared, and then rearrange the equation. The L squared cancel out with the L at the top, right? So this is the dimension of the A. So according to this is actually in terms of the formula, okay, the A is equivalent to V squared over the formula. Okay, what is the symbol? The formula is talking about radius, isn't it? So the symbol is R. So this is a formula of centripetal acceleration. So see, this is on how we derive an equation from a statement given by using dimensional analysis. Right. This one, take it as your homework. Okay. Now I want to show you another purpose of using dimension analysis. The third purpose is to derive an equation from a given concept, or we call it as power law. Take a look at the question given here. A student performed a simple pendulum experiment. The student observed that the period T is depending on the gravitational acceleration G and length of the pendulum. Supposed length of the pendulum L. Right. Derive an equation from this observation. So in terms of statement here, a very long statement here, we can put it as proportionality in terms of the period is depending on the gravitational acceleration and the length of the pendulum. Okay, how it is depending on? Is it inversely proportional? Is it directly proportional? Is it depending on the square of L or what? So we don't know. Okay, so we don't know. When we don't know, we put the unknown, the power of the item that we don't know, okay, is X and Y, the unknown. Alright, how about T? Does T has any power? Yes, 1. How we know the T, the power for T is 1? Because from the statement given, the period is not period square, right? It's not period power 3, right? So it's the period. So means that it's only power 1. Okay, now we are going to convert the proportionality into the mathematical expression. So T is equivalent to, when we have an equivalent, it must be a constant in front, isn't it? So let's say a constant of K. I put it as general. You can use any symbol. K, M, A, B, C, whatever the symbol is. Okay. G power X dot L power Y. I'm going to use dimension analysis first thing first. And then finally, I'm going to substitute with the SI unit. And then the dimensional symbol and simplify whatever I can. And then figure out the unknown of X and Y. So the dimensional analysis of both sides going to be applied. Okay. And for the period, the dimensional symbol T as well, right? Oh, very lucky of us. Okay, when we are using dimensional analysis, we are not concerning about numerical value. The numerical value, the constant in front of the equation, now can be dropped because the constant has no units. Remember, 1.2, 0.5 has no unit because dimension talking about units. If there is no units, there is no dimension for it. Okay, so we're going to drop it. Okay, vanish it. Right now, okay, the dimension of the G. What is the G? It's meter per second squared. How we know it's meter per second squared? Because the statement is talking about acceleration, gravitational acceleration. See? And don't forget that it has power x. Dot with the length. What is the SI unit of the length? Meter, right? Power y. Okay. Now, simplify whatever we can. M power x as negative 2x dot m power y. Then, combine the m. Don't forget the bracket. X plus y dot s negative 2x. Okay. Now, we're going to replace it with the dimensional symbol. M, meter, is representing length. So, L power x plus y. And the S is the second, is the unit of the time. So, this is T negative 2x. Don't forget this side, we have T. Alright. Now, okay, I'm going to do rewrite it again here. T equivalent to, remember T power what? Power 1. T also 2x dot L x plus y. So that we can see it clearly, right? So, but then, if you take a look on this, there is no L at this side, isn't it? So, is there actually any L at this side? Yes, actually there is L at this side, but the L power 0. Something power 0 equivalent to 1, right? Okay, so now we are going to compare the power. Okay, that is why we call it power law. Okay, compare this is our step. So we have for T, okay, for T, we have 1 equivalent to negative 2x. You see? For the L, we have 0 equivalent to x plus y. For the x, firstly, isn't it? X equivalent to negative 1 over 2. Once I have the x, I can solve for y. Y equivalent to negative of x, where I'm going to have negative of negative half. So, it's equivalent to half, isn't it? So, we already have the x equivalent to negative half, the y equivalent to half. Now, these two information, I'm going to substitute it into this equation. Alright? So, now, the T equivalent to K, G, power x, multiple with the L power y, which is half. Let's put it better way. Rearrange it. K times with the half, it means that square root. This is positive, this is negative, means that L over G. Negative part of the dimension analysis, it cannot give you any numerical value. Period of a simple pendulum is equivalent to a constant, symbolized as K here, square root L over G. For those who still remember, the period of a simple pendulum, T is equivalent to 2 pi square root L over G, right? So, the numerical value of 2 pi here cannot be obtained by using dimension analysis only. You have to have another step. However, this is for A level or for Form 6 level, STPM. They are going to plot a graph and figure out the numerical value, the constant. where it gives you the 2 pi value. Alright, so that's it for the third purpose of using dimensional analysis. Let's move to the subtopic conversion of units. Alright, so unit conversion always involve a conversion factor. So here's some of the conversion factor. You may use your calculator listed there, the conversion factor. Actually, you don't have to memorize. Use your calculator wisely. Alright, so this is on how to convert. Hopefully you still remember on how to do this. And this is the powers of 10, the prefixes, the abbreviation, the prefixes. Also, you may refer to your calculator. You also have all this, actually most of it from your calculator. This is one of the example on how to do the conversion, right? So the traffic light turns green and the driver of a high performance car slams the accelerator to the floor. The accelerometer registers 22 meter per second squared. Convert this reading to kilometer per minute squared. So this is on how they convert it. So you see here, you have to make sure all the units cancel out each other and then finally left with the unit required by the questions. Okay, hopefully you are okay with this. So take this as your homework.